We gotta get the Desmos up and running, maybe. Let's get this going here. Ooh, baby. Don't want to blind you guys. All right. Charlotte is awesome. Thank you for saying so. That's very kind of you. You'll love to see it. All right. I think we're getting YouTube going now. Yep. Wait, let's get, there it is. There it is. We got to pop out the chat for myself. All right. Pop out the chat. Here we go. All right. I think we're pretty well set now. All right, so gotta keep an eye on Instagram because I think some people do pop in on Instagram, which is surprising. All right, we are, let's see, 6 minutes away from this print finishing here. And I realized that I can further optimize this design a little bit. So what I've done here is I'm cutting into this just enough so that we pretty much have the minimum wall thickness here, because this is not load bearing, this part. We really just need like the minimum possible wall thickness. And I'll set a goal. Nobody sends me super chats, which is sad, but I'll just set a little goal. You know what? It's going to be 100 push-ups still. I'm just going to keep it at 100 push-ups until I actually do push-ups. You know, until I actually do the 100 push-ups, that's still going to be my goal. Why would I change the goal? All right. Please let me do 100 push-ups. Okay, so 0.8 millimeters, that wall thickness there. And what that allows me to do actually is what I have done is I've extended the diameter of this wheel so that it's further preventing the string from getting stuck in between the reel and its pillow block here. Hopefully that does the job. And let's see here. I think what I can do also is fillet this a little bit. Like whenever I edit these designs, it's always like that's right. For the push-ups, yeah. Whenever I edit these designs that I've been working on for a long time, it's like, I don't know if I should like try to keep like a Bible or something like that, like a design Bible for a specific project or something, but that would just be too hard. I don't know. I keep all the things in my head. Like if I'm like, because if I want to do A, but B is preventing A, and then like, 10 weeks later I come back to the design and I'm like, oh, why didn't I do A? I should have done A. Let me do A. But I completely forget that B is preventing A. And yeah. Thanks for stopping by, Instagram dude. Appreciate it. Yeah, so hopefully this is not going to cause any problems. I don't think it will. And I'm also wondering about this design here. Like the way this spring hooks in, I feel like could also be optimized a bit to make some more space for the tension spring that goes on this little tab here. because sometimes it falls off. It's not the biggest issue, but since I'm about to print this part, I'm kind of thinking of all the potential issues that I might come across. Okay. No, not that one. Oh, I hate when this happens. It's not parallel. Okay. So what we do instead, in this case, is we end the sketch. Then what we got to do is split the surface into, this is sort of like an intelligent extrude method when your extrusions are like not exactly perpendicular. They need to not be perpendicular to the surface you've drawn the sketch on. I think this will work. So let's see here. You split the face. That's the face. That's the splitting tool. I think this will work. I think we need, you know what I should have done? I should have, hold on, let me edit the sketch here. Trim that. Okay. Now we're going to look at splitting the face. All right. Okay, this one and that. Can I select multiple splitting tools? No, I cannot. And I don't want to extend this because I think it's going to be enough. But then, look how many sketches there are already. And this is after exporting as a step and re-importing. Oh my god. Okay. Split face. Split that face with that tool. Okay, now we do press pull here, here. And what are you doing? Oh, that. Okay, I think it's because this I actually selected the sketch and not the face. So let me do that real quick. Thanks for stopping by, Moises. Nice. Hi back. I hope you have a beautiful sleep. There we go. It's kind of doing what it's supposed to be doing, except not perfectly. That's a shame. Oh, that's weird. This will probably be good enough. It's kind of messy. We're just going to smooth over some of these edges. Thanks very much. It was a fun little ceremony there. And I'm flexing my degree for everyone to see. All right. This should be pretty decent. I'm almost wondering if I could press pull this a little bit more. I don't know if this will work. CAD gets pretty finicky. Yeah. Just to give this tab a little bit of extra stiffness. Maybe, yeah, adding 0.3 millimeters is probably good. Okay. And that part is now done, so I need to get another one started. But I don't believe, oh, there is, yeah. I just finished fixing this one. So we're going to go ahead and print that one. Let's see here. Okay. Yes, this part. Okay. Now let's watch what happens when we reload this. All right, a little beefier there at the bottom. That'll be good. Good for the design, good for constraining the spring. We just want to make sure that this is nice and smooth when it gets printed. It's like almost like I don't actually want the elephant foot compensation for this part, which is crazy. But it actually kind of messes with the parts manufacturing, or the part shape once it's complete. I also feel like for this we need to be a little bit careful about the layer cooling time. So what do we got to do here? It's not filament overrides, it's printer settings, extruder 1. No. General? Or is it filament settings? Cooling. There it is. Okay, so if it's enable fan if print time is below 20 seconds, I mean, yeah, that's correct. But below, slow down if print time is below 20 seconds, and minimum print speed, call it 8 millimeters per second. And we're going to have the maximum fan speed here be really high. Great. All right. And I also am kind of like the support material that's under here. I don't, what do they say? I don't trust like that. I don't trust like that. So first of all, layers, first layer height, we're going to bring that down. And then USS Nate, thank you for supporting, my man. Appreciate it. Glad you're back. All right. That's crazy. Okay, let's see here. Okay, what was I doing? Okay, I need to exit the photo app because this is ridiculous. The layers, that's right. Okay, so bring down the first layer, and then in terms of support material layers, I'm going to bring down the top contact Z distance, and we're going to bring pattern spacing, you know, and we're going to make this snug. And pattern spacing is going to go down to 0.8 millimeters. I don't think that really matters because there might be only one layer, but that's the thing. I want to make it not only one layer. I want to make it like 3 layers. So XY separation between an object and its support. What am I looking for here? Interface pattern spacing. I feel like just bring that down too. Closing radius, not 0, 1. You know what? We'll bring this down. And closing radius. I'm also like the bridging. I feel like the bridges should be cooled more. I'm taking great care with this part, but I also don't really know if anything that I'm doing is a good idea. But we'll see, I guess. Okay, what do we got? Okay, now, good. We've got 3 layers on the bottom here instead of just 2. That's nice. Okay, support material has quite a few more layers. That's good. It has 3. 1, 2, 3. And then the part. Amazing. Okay. Yeah, we're gonna try it. I'm also like, this infill's kind of whack. I'm wondering if I should do different infill for this part. Concentric. Interested what octagram spiral is. That's interesting. Whoa! It's pretty weird. I also don't like how it doesn't actually touch the center. That doesn't seem correct. I feel like we need something that is axisymmetric, though. So that's why it's tricky. I mean, I don't know if concentric really does what we need it to do. Yeah, it's just hollow, basically. Which maybe that works, maybe that doesn't for this part. I don't know. I don't know. Hilbert curve is interesting. I heard that's supposed to... What is this, man? What are we doing here? What is this? What is this shape? I feel like that's not what is... Photos. Stop. Can we get this... There we go. Okay. So what is going on with this this Hilbert curve? What are we doing? Okay. Infill. Taking way too long with this. But cubic, stars, rectilinear, lightning, Archimedean chords. And they're like, ooh, that's interesting. What are Archimedean chords? Let's find out together. Okay, it's a 3D infill pattern. I get it. Archimedean spiral. Stop it. Why is the Photos app opening? Here's what I need. No, you know what? Yeah. We need to set these preferences here. Because it's, for some reason, it thinks that my phone is like disconnecting and reconnecting. So this is the top infill pattern for Archimedean chords. That's crazy. That's pretty interesting. I guess, yeah, I mean, it's nice for circles. It's nearly the same as concentric. So this is a concentric, like a continuous spiral, which, okay, I've actually been looking for this for a long time. I didn't know they had this. Because, yeah, this is great for a circular object. Like, I didn't know they had this. So this means that, like, it's like concentric, but the printer never stops. And if the extruder ever like stops moving, you get rid of a lot of the parasitic effects that come with 3D printing. Okay, so if Photos opens one more time, I am going to figure out how to stop it from automatically opening if it detects that a phone is connected, because that's pretty stupid. So this could be good also for the top and bottom, though. Top fill pattern, Archimedean chords, bottom fill pattern, Archimedean chords. And if we just turn this up a bit, I wonder what we get. Let's see what it looks like. Like, it doesn't look like it's doing anything different for this part, which kind of makes sense. What do we got here? It doesn't look very different. But I guess we'll see. Yeah, there's that spiral in there. I have a feeling this will lead to a better result on the outer surface, given the continuousness of it. And this is a 46-minute print, so this is going to take a minute. But we have to get this part right. That is very important for the functioning of this thing. All right. I am going to be back. In the meantime, you can watch this. And maybe let's get some... well, I know we got some music here. All right, be right back, y'all. Ridiculous. Cut the music. Cut the music. We're not... No, cut it. Stop. Okay. Nothing going on there. Okay. How to get Photos to not automatically open on Mac when phone is connected. Easy. That should solve it. That should solve it. All right. Sorry about that. Okay. What are we doing here? Right. Okay, that's done. So we're nearly done with this design. The very, very last thing is the fact that I'm worried about the rope like causing a lot of friction when it's pulled out. So what we have here is a set of washers that gets press fit into this side. And so the rope making contact with the metal should be far less friction than making contact with the plastic. So hopefully that's good. And then the very last thing is I want to do the same thing but for this side here. And I've got some pretty thick steel dowel pins. So I don't know if they're too big to fit, but the larger the radius, theoretically, the better this will work. I think that's capstan physics, right? So like, let's look this up, guys. Capstan friction calculation. Capstan equation, classic. Okay. So T load, T hold, and so the ratio between the holding force on one side of the capstan pulley I wonder if there's a derivation for this equation. There is. That's so cool. Okay, we're going to go through this someday. Hopefully. I don't have time right now. If it was any other day, I would totally take the time to walk through this derivation, but that's pretty dope. That's so cool. Okay, so the ratio between, this is, by the way, is a capstan pulley, right? So that's funny. An example of when knowledge of the capstan equation might have been useful. Yeah, so this is like when you're pulling a cable through a tube like this. So for instance, T hold, like for us, wish I could draw on the screen, honestly. That would be kind of cool. Let me see. Okay, we definitely... Why are we night mode? Unbelievable. Probably have to change Chrome preferences, which is kind of silly. This seems wrong. I'm not going to open that. Okay, it doesn't really matter. So this essentially is like, I'll just put a white square behind it. That's actually pretty easy. Great. Okay, so let's see. It's a flowchart editor. I don't know why I opened this, to be honest. Choose like this circle thing. Whatever. Ugh. Okay, so T-load for us. This is basically the tension. Black text, please. This is the tension on the side of the reel. And this is the tension on the side of the projectile. Okay, and this is essentially like our slider. So like our rope needs to pass through from the spool. So that's T-load. And then the projectile pulls it out. So that's T-hold. Okay. And you can see if there's no friction, right, these would be the same. The tension would perfectly equalize. But there's friction between the rope and the capstan pulley. And so T-load would almost certainly be greater, or rather less than T-hold. Yeah. I believe so. Because mu is the coefficient of friction. Phi is the total angle. And so if I draw this out in Desmos, T-hold as a function of, all right, T-load as a function of T-hold, we get we get e to the phi times mu. I wonder if, let's call it u. Okay. Times T hold. Okay, so it is, we need to figure out that slope, basically. So when the angle, so let's make the angle between 0 and 2 pi with a step of pi over 100. Pi over 10 is probably fine. Okay, and then mu is just between 0 and 1, right? Am I goofing? Here we go. Yeah, occasionally it's maintained that mu is always less than 1, but it's not true. That's what I thought. Most relevant applications, right. Yeah, silicone rubber, acrylic rubber coated surfaces have a coefficient essentially greater than 1. So here's some examples of coefficients of friction that are greater than 1. But it looks like the maximum that we have here is like 3. Platinum, platinum? That's cool. Is that real? Why are they talking about this? Concrete and rubber is less than platinum and platinum? mean, this is a pretty large coefficient of friction here, but they're all cited, mostly. Interesting. Okay. I mean, you can see that this slope of this line, e to the mu phi, is greater than 1, it seems like, which means that T load is greater than T hold, which is interesting. But let's see what it actually looks like when you're changing the angle. So for instance, start with no friction, they're equal. The slope of the line is 1. No angle, also equal. Slope of the line is 1, because that's e to the 0 is 1, right? Okay. So it doesn't look like, yeah, there's no way to get this to be less than 1, obviously, because the exponent would have to be a negative number. Duh. Sorry. Okay, so yeah, that means that for this, the way they framed it, T load is the applied tension on the line, T hold is the resulting force exerted on the other side of the capstan. Okay, so they've kind of reversed it. Fine. Yeah, and we want to minimize that tension on the projectile side, because that's going to be more than the side of the reel when it's being pulled out. So if we have, so for instance, like, let me draw this out in Fusion real quick. The shape will always be like, say the rope needs to pass through there or through there. So here, technically, like the difference between that capstan and that capstan is not very much, because the angle will still be 90 degrees. So in our case, because the angle is the same and the coefficient of friction is the same, so like the rope going like this over that capstan technically shouldn't have more friction than the rope going over this capstan. And I do have some smaller pins here that I can use as well in case these big ones don't fit. I don't know, I'm wondering if I should even use the big ones if the capstan equation doesn't allow for it. But what I'm going to do is I'm going to look at this. It's a pretty rough shape, to say the least. That string has to pass through right there. But it's kind of like this corner that the rope is going to be rubbing against. And so you can see why that would cause a lot of friction. Yeah, because the rope is just going to go straight through there like this. Crazy. Okay, I need time to think about this. So I'm going to, let's see, is it possible to pause a stream? No, it's not. So I'm going to stop. Excuse me. And we're going to come back. We are going to come back. Promise.